The chance to shape your future is here. Learn and connect with exciting new opportunities. Are you ready for the next step?
Okay, well, welcome everyone, and thanks for joining us to learn all about the mysterious world of quantum. I'm sure we've all heard of quantum mechanics, quantum physics, that have been lurking around for many, many years, and in quite a mysterious world that sometimes is brought to life by the likes of Professor Brian Cox and many years ago by Carl Sagan. And you may well have come across terms such as Schrödinger's cat, Heisenberg's uncertainty principle, and entanglement. Well, some of these will be discussed today, but essentially since the 1960s, a lot of progress has been made, and a lot of it's based on semiconductor technology powered by silicon. Really silicon ushered in the digital age as we know it now. But there's now a new generation of semiconductors, compound semiconductors, that are introducing a new range of technologies based on quantum physics, where the digital world of ones and zeros is about to be completely transformed. So from quantum computing to miniature atomic clocks, sensing, imaging, and security, the mysterious world of quantum is about to be unveiled. So hopefully some of the terms will become a little more familiar to you by the end of this session. I'm going to introduce a number of speakers. We have David Kerner from Innovate UK, who'll be talking about the UK investment in quantum. The UK is actually leading the way in terms of quantum technologies around the world. We'll then be hearing from Ali at the CSC, the Compound Semiconductor Center, on quantum photonic components, also known as QPCs. We'll have a talk on atomic clocks and very accurate timekeeping and the role that's being played by quantum, presented by Moss. And then single photon detectors for detecting mid-infrared sensing and for imaging technologies. And that'll be presented by Adam Craig of Amethyst Research. And finally, quantum key distribution, QKD, cryptography on communication systems from Mark Stevenson at Toshiba. And then we'll wrap up with a panel session, a Q&A with all of the speakers. So without further ado, I'd like to introduce David from Innovate UK to talk about the investment in quantum in the UK. Thanks, David.
Thank you, Chris. So thank you very much for inviting me to speak. I'm going to be discussing quantum technology, giving an introduction to the UK scene. I'm one of the innovation leads at Innovate UK on the Commercializing Quantum Technology program. So in terms of what I'm going to cover today, I'm going to give a very brief overview of what quantum is, what we mean when we talk about quantum technologies, why does it matter, how we think quantum is going to change the world, and the impact it's already having across the UK and the world. And then what's happening in the UK? What are we doing to stimulate quantum technologies to ensure that we capitalize on our position? And finally, a call to action for Wales. So you can probably tell from my accent that I am a Welsh man. I grew up in Swansea and I live in Cardiff. Makes me rather conflicted on football days, but I want to discuss Wales's position in this market and how it can be strengthened. So very quickly, what is quantum? Most of you are probably aware that quantum mechanics of the kind that was discovered at the start of the last century has already been well embedded in devices we use day in, day out, things like lasers, LEDs, semiconductor transistors. But what we talk about when we mean quantum technologies is really ones that make use of the really exotic quantum properties that we're really just beginning to harness and properly understand how we control those properties. By those we mean superposition and entanglement. I tried to make a couple of slides covering an introduction to these before I gave up and realized it was going to take up all of my 10 minutes. But the interested reader can go away and find out a few things about what they mean. One of the difficult things in describing these is that there's really no macro analogy, nothing that we see in the world around us that behaves like these quantum systems. So we describe them as exotic behavior because we don't see anything like it in the world around us. And that's why it's been difficult to harness these things and start to learn to control them. But those technologies are emerging right now. The first products coming to market. This is no longer just research. This is an industry that is emerging. And I'm going to talk through a few of the key technologies which are coming to market now. Those being quantum computing, quantum secure communication, sensing and timing, and imaging. As you can see on the right there, there's a whole range of areas where these technologies are going to be transformative. And really in the short, medium, and long term, quantum technology is going to have massive impacts on all of these areas, which are really the big challenges facing humanity at the moment. So first of all, quantum computing. This is really making the use of the superposition qualities of quantum systems. That means that in a digital system, you might have ones and zeros. In a quantum system, a qubit can be in a combination of that 1 and 0 state at the same time. What it means is that your computer power scales exponentially with the number of qubits you have. And what that means is with just tens of qubits, you're looking at quantum computers that will exceed the power of the biggest supercomputers on Earth today. And we've already seen that. You can see on the right there some of the announcements from the last few years. Google achieving quantum supremacy, so performing a calculation faster than any supercomputer on Earth could ever hope to do it. And physicists in China announcing quantum advantage. That means they've done a useful calculation faster than a digital computer could do, or that we couldn't hope to do on a digital computer. What that unlocked computing power means is that areas where you need that access to massive amounts of computing, high performance power, are going to be making use of that and are making use of it right now as we speak in things like drug discovery, finance, weather and climate forecasting, material development. Another important thing which will happen with the emergence of quantum computing is that they will render modern encryption techniques obsolete. So all of the encryption we use in our communication is based on mathematical methods which cannot be cracked within a sensible time frame by modern computers. Quantum computers will make short work of those encryption methods. And it's really building towards becoming a critical issue because, of course, communications we send today using those encryption methods can be cracked in the future by anybody who's storing them. So we need new secure communication methods. And quantum also offers a solution here. So there's two real elements of quantum secure communication. That's new algorithms, new mathematical algorithms that will be resistant to attacks from quantum computers, but also quantum key distribution. So this is using the entangled properties of photons to send communications which are inherently secure. They cannot be intercepted. And as you can see on the right there, there's already a lot of activity in the UK around this, and we'll see some more of it later from people like BT and Toshiba, who actually recently located the manufacture of their quantum key distribution systems in the UK for both fiber and satellite-based communication. Quantum sensors and timing. The sensitivity of these quantum states to their environment means that they do make excellent candidates for sensors. So there's lots of applications you can see here, surveying, climate and earth science. But I want to just give one example in healthcare on the right here. So this is OPM, that's optically pumped magnetometers. These are quantum devices which we're looking to replace the current generation of functional brain imaging, imaging what's going on in your brain. You can see in this image on the right, a conventional magnetic encephalography machine, the way that we currently do these measurements. It's big, it's bulky, it's expensive, and the person in that machine can't move for the entire duration of the measurement. The new generation on the right using these optical sensors, they can be put on a device that looks like a swimming cap. They're about the size of a Lego brick. They will cost a fraction of the device on the left, and that person can be moving around while these measurements are taken. That means people who have involuntary movement can still access this imaging and any treatment it unlocks. And of course, it means that people can be performing tasks while measurements are taken. So this is just one example of a technology that's hitting clinical environments as we speak. Also mentioned quantum clocks. I think we're going to be speaking about this a bit later. But for chip scale, very high accuracy clocks, quantum offers solutions there, which are going to be critical in addressing the next generation of GNSS denial resistant technologies. Quantum imaging. On the right, you can see here a imaging system. This is a methane gas sensing camera being developed by a company called QLM through a project funded through in the Quantum Technologies Challenge at Innovate UK. This is a camera. Methane is a tremendously powerful greenhouse gas, and a huge contribution to our methane emissions are leaks from industrial facilities. This device is cheap, it's lightweight, it's portable, and it can be deployed in industrial settings to image those leaks in real time, so that industry, who are also very motivated to address this because it costs them in the order of billions of pounds a year in wasted material, they can be getting out to repair leaks as they appear, rather than having to manually look for them using non-direct imaging techniques. So what is the UK doing? What does the UK's programme look like? So the National Quantum Technology Programme is a £1 billion 10-year investment that's been running since about 2016. That's brought together the organisations you can see on the right, but industry, government and academia all linked up. And what that's meant is that this model that we've used in the UK, by joining together all these partners, has really led the way in terms of how other countries have approached quantum technologies. They have imitated us to a large extent, which reflects the success we've had. In terms of how that money's been spent, you can see the big orange chunk here. That's our industrial program, which I'm involved in. The blue chunk here, which is the academic program, really the quantum technology hubs and centers for doctoral training, as well as the National Quantum Computing Centre there, the grey slice, which is a new venture really. Those quantum hubs, they cover the technologies we've discussed of sensing, communications, imaging and computing, and they really do span the whole of the UK. These are really the interface between academia and industry, really planting the seeds for projects which eventually will become business-led industrial projects, which is really where the industrial challenge where I sit comes in. So we are currently in the process of deploying £153 million of government support for the commercialisation of quantum technology. We've deployed about £70 million of that funding, and you can see the distribution of that spend in the slide here. To give you a sense of what one of those projects looks like, this is one project. This is actually led by Toshiba, the Aquasec consortia. We've got 16 partners spanning big international majors. We've got BT in there, systems integrators, end users, and academia, component developers. So you can see here the complexity of our consortia and how much work is going into these projects right now. This project is actually to deliver QKD over fibre networks in the UK. So in terms of the opportunity in quantum, I want to quickly mention this. We are currently in the process of our next round of competitions to be awarding money for industry-led projects to develop quantum technologies. That spans feasibility studies, small germinator projects, and big collaborative R&D projects. Those competitions are opening as we speak. And that really leads me on to my next slide, which is a call to action for Wales. So we're already seeing an emerging market for quantum technologies in Wales, but I think we could be doing more. What we do at the moment is quite narrow, and I'd like to encourage you that if you're interested in what you've heard and you think as a business you're interested in quantum technologies, to engage with us. My email address is on the screen. We're an accessible team and we're very happy to talk to you about what quantum can be doing for you. And that's all from me. Thank you very much.
Thank you very much, David. Great overview, and really positions the UK as the world leader that it is in quantum. And I'll come back to that as a question as to why we think that may be in the panel session. We do have questions on GPS and on quantum ICs, but I think these will be addressed in some of the later presentations. So if they're not picked up, we'll move them to the panel session at the end. So now I'd just like to introduce Ali from the Compound Semiconductor Centre, which is a joint venture between Cardiff University and IQE, based in Cardiff. And Ali is going to talk about QPCs, or quantum photonic components. So over to you, Ali.
Thank you, Chris. Hello, everyone. So as Chris has already said, I work for the Compound Semiconductor Centre here in South Wales. I'm the Programme Manager for Photonics. And what I want to talk to you about today is really moving from a custom model for R&D for custom devices, if you like, for quantum, towards a commodity model where we've got devices that people can use that are robust, reliable, and cheaper. So that's one of the messages I want to get across to you. The main message today is really that quantum is here to stay. Quantum is developing, and R&D is in full flow. And that industry is now thinking about how we service the quantum market. So what we need to think about is, how do we bring those components to the market at a reliable and a robust manner, ready for manufacturing. So today I'm going to be talking about quantum photonic components, QPCs. There's one thing you should know about quantum, and that is that really without photonics, we can't do very much quantum, if any at all. And the other thing you should know is that the photonic components we're talking about require compound semiconductors. So really, without compound semiconductors, we can't have the photonics, and without the photonics, we can't have the quantum. So this is the bottom line here, and we're a compound semiconductor and materials developer. So if I just go on to the next slide, as Chris has already mentioned, we're a 50-50 joint venture company, Compound Semiconductor Centre. We're set up in 2015. Cardiff University, our co-owners, have a history and pedigree in semiconductor and compound semiconductor R&D excellence. And IQE PLC is one of the largest, if not the largest, provider of epitaxial compound semiconductor materials worldwide, with 10 sites across the globe. In all the continents, in the Northern Hemisphere at least. So yes, and we were formed really to help with the translation of research into commercialization, into the commoditization of compound semiconductor research and development. So in 2015, there was several £million invested both by Cardiff and IQE into Compound Semiconductor Centre in St Mellons, Cardiff. We run over a dozen reactors, as we call them. You see a picture of one in the middle of the slide there, an 8-stron reactor. And these are metal organic chemical vapor deposition reactors. And what they do is essentially, if you have a look at top right, there's a substrate there. The substrate is like a CD, I describe it. It's a shiny CD. But it's a specific material such as indium phosphide or gallium arsenide. And what we do is we put that into the reactor and we atomically engineer and grow on top of that very, very thin atomic layers of various compound semiconductor materials according to a specific design. And for photonics, there are various different device architectures, and according to the device architecture, whether the laser beam comes through the top of the device or the side of the device, you have different types of material species grown in very specific orders. And every time you want to produce a new device, you have to come up with a new epitaxial layer design. So epitaxy is the actual growth of the material, and the layers then are grown one by one. And so those designs change depending on the application or depending on the end use. Okay. So CSC is primarily a collaborative R&D entity, and we work closely with industry and academia. We supply epitaxial materials primarily for product development and R&D both privately funded and grant funded, such as I will describe today in some of the projects I'm going to talk about. I just wanted to talk very briefly about Strength in Places as a funding that we won. It's a UK government grant funded. In South Wales, we have a cluster. It's the world's first compound semiconductor cluster. You can see that we've got the two universities, Swansea and Cardiff, David, so you'll be happy about that. So we've got, we've got the two universities, both massively involved, particularly in the last decade of doing nanotechnology R&D, and they've got brand new centres, shiny new equipment, based on years and years of historic achievement in R&D. We've got the materials growers at the bottom, the epitaxial material growers, CSC, ourselves, and IQE. But we've also got the fabricators who take those wafers, dice them, and develop them into devices, which are then packaged, for example, by the company Microchip, our partners there in the cluster. They can be characterized and tested by the catapult in Newport, the compound semiconductor applications catapult. And so you see we've got a cluster, the world's first compound semiconductor cluster in South Wales. And we're really here to focus on developments in compound semiconductors, but particularly in quantum at this moment, because quantum is providing massive opportunities for photonics development, for compound semiconductors development. So I'd like to talk to you about a few of the projects that we've got going on at the moment. So I'm going to introduce to you three projects, which I call the custom quantum photonic component projects. And then I'm going to talk to you about the project that really is looking at the commoditization of this. So without further ado, the first project we call QBAT. Here we're trying to develop, as David already introduced, an optically pumped magnetometer, and these OPMs use compound semiconductor lasers. So the partners really, if you'll notice, these projects all have supply chain level of involvement from the partners. From the top, we've got the epitaxial materials growers ourselves, all the way around to the end user, the battery manufacturer. And what we're doing here is we want to scan batteries as they're being manufactured and being tested, ready for release. Ampty Power, based up in Scotland and in Oxford, have these batteries, and we're going to monitor the quality of the batteries by looking at minute current discharges, looking at the magnetic field from those using very, very sensitive magnetometers. So you can see a schematic there. We use translator battery on a conveyor belt underneath what we call an OPM array, and the magnetometers build an image of the discharge of the current. They can say what quality the battery is. If it's a high-grade battery, it will go to a high-end, perhaps an automotive or a aeronautic end use. And if it's not high quality or high grade, perhaps a less critical use. But still, you can grade them from good to excellent. So in the OPM, the schematic in the middle shows at the top there's a laser. And if you have a look at the left-hand side of the slide, you see the value chain from us at the top, producing these wafers, to the wafers being developed into individual devices, which are 1/4 of a millimeter by 1/4 of a millimeter, to then being packaged, then going into this OPM. And on the right-hand side, you can see Kelvin Nanotechnology, one of the partners in this project, builds what we call the gas cells, the cesium vapor cells, and it's the interaction of the magnetic field with the spin of the cesium atoms in that cell that really affected the light going through the cell and tell us how much the magnetic field is changing. So it's a polarimetry-based system looking at the change in the polarization of the light. So this project is really a custom development project. We're developing the custom materials for a custom laser, for a custom OPM. But in order to scale this up, we really need to move forward from that to a commoditization model. The next two models, so apologies. So here we can show you the supply chain from us producing the wafers on the left-hand side, right away to Ampty Power on the right-hand side, who use the magnetometers, and even Cosworth, the famous automotive engineering company, who are looking at electric drivetrains, who will then use them. And we've got the capability in the UK to capture the full full supply chain. My colleague Mohsen from MPL will talk about this particular magnetometry project. There's another one we're involved in, very similar in terms of to the previous one. We supply the epitaxial materials. Again, you can see we capture the full supply chain. Again, another custom development project. Another one still, which Mohsen from MPL will talk about, is the atomic clocks project, Kairos. Again, another custom development project. So now I want to talk to you about QFoundry, which is the looking at commoditization of the quantum devices. So far we've been talking about custom development and looking at individual projects. What this lacks is robust, reliable, and a volume supply of these quantum photonic components. It's expensive for R&D because each of these projects, over £1 million of each one perhaps, is associated with the compound semiconductor photonics aspects. And that's not scalable, because if you're going to do that and the cost of R&D are so high, the market traction will be slow. And also in the R&D, the developments that we do at a custom level, which will mean that we don't have enough aggregated data in order to introduce reliability into the manufacturing of these things. So it comes along QFoundry. We've got partners across the UK, but you'll see that cluster in South Wales. We've got Cardiff, CSC, IQE, the Compound Semiconductor Catapult, CS Connected, Microchip, and we are all at the front end of it, producing the materials right the way to testing, characterization, packaging. We are involved in one of the streams of this project. And really what this Foundry project is trying to do is to address critical sovereign capability in the UK, in Wales, enabling rapid prototyping. We are doing the reliability and the manufacturing aspects, designed for manufacturing aspects of quantum photonic components, so that individual projects don't have to do that, and that we can bring the cost down to build up market traction. So that's what really the Foundry project's all about, and we're the first ones in the world, as far as we know, that we're doing a Foundry approach and hoping to take that into other countries and build up our strength. So the three main, if you like, requirements in terms of photonics that we've identified are the top one is the set lasers, which we are very much involved in, the compound semiconductor lasers, which are called VCSELs, vertical cavity surface emitting lasers. Look that up if you're interested, please. But also for quantum, you'll find that a lot of quantum projects require single photons. So we need single photon quantum emitters and single photon detectors. And this is where our partners in the Quantum Foundry project from Toshiba, from Cambridge, from Amethyst, Lancaster, and some of the other partners you saw on the map, MPL, come into play. So we've got these three different streams. These are the three main streams of quantum photonic components that we've identified for commoditization. That brings me to the end of my talk. I apologize for running over. It's very exciting. There's a lot to say. So I hope that's given you a flavor of what we're trying to do in terms of aiming for industry growth and manufacturing in this area. Thank you.
Thanks, Ali. Very grateful for that, and no worries at all about running over. I think it is an exciting story, and I think it puts into perspective, as will the next couple of application presentations, how this is becoming real. You know, we've talked about quantum for a long time, and in some ways I liken it to lasers, in that you know, Einstein originally came up with the idea that lasers could exist, but when the first lasers were developed, I think it was really a solution looking for a problem. I think we've moved beyond that stage now, and there really are real-world applications, as we're seeing today. So thanks again, Ali, and I'd like to hand over now to Moss from the National Physics Laboratory in Teddington, who's going to tell us all about applications such as atomic clocks and magnetometers, as Ali mentioned. So thanks, Moss.
Yeah, thanks. Just checking you can see the screen, the slides I'm sharing.
Not seeing them yet, so maybe the same as you are sharing. So hopefully Jess is online from KTN, who can share them.
If you click on the bottom, there we go.
Ah.
There we go. We can see it now.
Ah, great, perfect. Okay, well, thanks for the introduction, Chris, and Hi all, so I'm Mohsin. I work at the National Physical Laboratory in the Time and Frequency Group. So at NPL, we do a lot of work in defining and disseminating SI units, a lot of which are generated by exploiting the quantum properties of atoms, where we use certain aspects of those atoms as fundamental constants, which we can then use to define things like the second, the meter, the kilogram, etc. So as Chris mentioned, I'll be talking about a bit about some application areas of quantum technologies and some of the work we're doing to help commercialize quantum products alongside UK industry. Okay, so this is a slide which shows some example application areas. David Cunner talked about some earlier with the brain imaging scanner using tiny magnetic field sensors on a swimming cap. But I guess the real advantage of using quantum sensors over standard sensors is that we get very high levels of sensitivity, and it enables a whole raft of new applications as well as improving on existing applications. So if I run through some of these examples, at the top there we've got onboard clocks for future satellite navigation systems. This is to provide timing services from GNSS satellites to things like the critical national infrastructure applications such as communications, transport, finance, etc. So having robust atomic clocks with very high levels of accuracy, as well as clocks which can actually hold that precision for long durations, so we call that stability. It's really important that we try and push the boat out in taking those technologies, making them much more compact so that they can be utilized much more widely and provide much more resilience to a number of applications requiring robust timing. Sensors for gravity and magnetic field is very important, particularly for surveying in oil and gas and minerals, and also for things like seismic activities and imaging things underground. Another type of imaging is using high sensitivity magnetic fields from a distance so that we can measure things without, so we can measure pipes underground, for example, without removing the insulation layers. We call this non-destructive testing. And this is really highly sought after because of the strides that people have to go through to actually detect corrosion under insulation. So in terms of the high-end quantum technologies, you can see the picture down in the middle there. That's a strontium lattice clock at NPL, and it's one of the most precise atomic clocks in the world right now. And we use this to provide a secondary representation of the second. Now, these kinds of systems can also be used to test fundamental physical theories. Very recently, some high precision atomic clocks were used to measure relativity, which was quite a breakthrough experiment. So I thought I'd have a go at explaining generally how we exploit atoms for quantum sensing systems. So I've put a slide together showing a periodic table which has a number of elements. And each of these have an energy level diagram, which you can see at the bottom right. I've picked cesium in this instance. And what this shows is some very discrete energy levels, which can also be represented as frequency. And these can be probed using laser interrogation. So if we have very low line width single mode laser diodes, then we can basically tap into these energy levels and extract the reference frequency from these atoms and use them to provide very precise sensor signals. And for quantum sensors, what we do with these energy states is we force, in this case, we force the two ground states of the cesium atom. So that's down at the hyperfine structure. You can see there are two lines there. We force them into a state of superposition, and that gives us an extremely high Q reference signal to give us an even more precise atomic sensor. So I've picked out cesium and rubidium here. These are atoms which have a single outer electron. And the reason why these are quite widely exploited at the moment with quantum technologies is primarily because the technologies required to extract the reference signal from these atoms in many ways are already quite mature. So for example, with cesium, we use a laser at 852 nanometers, which is very close to the telecoms wavelength. And by working on that laser design a bit, we can actually make it such that it serves in quantum applications much more readily than, say, a laser at a different wavelength. The other thing about the cesium and rubidium atoms are the modulation frequencies that are required to force them into a state of superposition are also readily available off the shelves through oscillator and microwave and RF technologies that already exist. So it makes these atoms very convenient for exploiting quantum sensor systems, but also enabling them to be much more, much easier to commercialize. So this is a general example of what the physics package within these sensor systems looks like. So at the top left there, I've drawn a schematic showing what goes inside a physics package of a number of atomic clocks and sensor technologies, where you have a laser diode, a vessel containing the atomic species of interest, and then a detector at the other end and some optics just to guide the light through that ensemble. A number of quantum systems, particularly in quantum computing and gravity sensing, use ion and atom traps rather than a vapor cell. But I've just drawn a vapor cell here just as an example. And at the bottom left, you can see a cross section of the physics package of a chip scale atomic clock that was developed a number of years ago, which comprises a tiny VCSEL chip, which Ali mentioned a moment ago, that's used to pump light through the atoms and reaching the photodetector at the top there. And I haven't drawn the dimensions here, but this is incredibly small. So this physics package is just under a centimeter cubed. And a similar physics package was made by a Japanese company a couple of years ago called RICO, who are also working on a compact atomic clock configuration. And in the middle here, this is an example of the reference frequency being extracted from these physics packages to provide a very high Q narrow line width atomic signal, which can be used to define a second, for example. And these can quite easily be used also as magnetometers by exploiting an effect known as the Zeeman effect, where these energy levels of the atoms can actually move slightly based on an ambient magnetic field. So Ali briefly mentioned the Kairos project, which is related to the manufacturing of and production and manufacturing of a UK-based atomic clock. So this is being led by Teledyne E2V in Chelmsford, and there are a number of other companies involved who are primarily there to develop a supply chain of components which can then feed into the production at Teledyne. So there are a number of critical components that determine the accuracy and stability of the atomic clock. And so what we're doing as part of this project is not only developing the clock itself, but working on these components to refine them and so that they can feed into the supply chain. But these components also give us the performance advantage to enable these atomic clocks to be much more competitive on a global scale. And similarly, we're developing a quantum magnetometer sensor, an ultra compact sensor that can be used for things like corrosion under insulation detection. And again, it's all about developing a robust supply chain of these critical components so that we can achieve the required sensitivity for it to be useful by end users. And that's all from me.
Excellent. Thank you, Mohsin. I think, again, it shows the scope, the range of quantum activities, again, moving from the lab to reality. So thanks very much for that. And I guess very closely related to that is single photon detection, particularly for mid-infrared sensing and imaging applications. So here I'd like to introduce Adam Craig from Amethyst Research. So over to you, Adam.
Thanks for the introduction. Yes, I work with Amethyst Research, who are a micro SME in the Kelvin Technology Park in Glasgow. I work for Amethyst at Lancaster University as a KTP associate, and I've been asked to talk to you today a bit about what quantum technology will bring to the midwave infrared. So a SPAD, a single photon APD, about which we heard earlier, or which are important to the wider goal of the Q Foundry, is a type of avalanche photon diode, or APD. And an APD is essentially a very sensitive type of photodiode. And the reason it's so sensitive is because it has this internal gain mechanism whereby charge carriers are multiplied under a strong electric field by impact ionization. And a SPAD is effectively, in some sense, the ultimate form of an APD, whereby a single photon can produce an avalanche of charge and hence be detected. And the single photon is effectively the last chance to resolve any information from your detector, be it an FPA or a single element looking for some kind of spectral signal. So a SPAD or a SPAD array was used to capture the. We've found the van from the clip art and taken a picture of it. You'll see in the bottom right there. No, we haven't. what we've done, this is a SPAD operating in the near infrared at 1.55 microns, and it's taken an image of this van in the bottom right. And what we think we'd like to do in the long run is develop a SPAD technology and array SPAD technology working in the mid-wave infrared. And the mid-wave infrared offers a series of advantages for these SPADs, these quantum devices, in the sense that generally SPADs operate using what we call an active mode illumination, and that means that the SPAD imager sitting on your warplane or other type of vehicle emits radiation at a certain wavelength, which is reflected from the scene and received back at the imager, rather than relying on solar radiation, that's just light from the sun which peaks in the visible, or 300K background radiation, which is black body radiation from the scene. And there's, I realized that the figure on the left-hand side is normalized, so the solar radiation and the 300K are not of the same magnitude, but there is this kind of sweet spot around 2 to 5 microns where solar background is lower and 300K background still hasn't kicked in yet. And a SPAD working at these wavelengths will allow us to use active imaging with increased effectiveness. And in addition, there is this pair of atmospheric transmission windows. So water in the atmosphere absorbs pretty strongly at various bands within the midwave infrared. But there are 2 specific bands between 2 and 2.4 microns and 3.5 and 4.5 microns, where this is not the case. And a SPAD operating in these windows would be able to penetrate media such as clouds, smoke, snow, or smog, where water vapor was obscuring the scene, so that you could image through these media. You can see an example of this in practice. This was done. This is from the literature. This is an image in the center here where you see 6 hot glow bars, and these were imaged using a midwave infrared camera through a smoke screen. And you can see that the 6 reproduced on the right, where they're completely invisible to the naked eye in the visible scene below. So what would quantum technology bring to midwave? Well, it would allow you access to these wavelengths which allow you to see through obscure media. It would allow you to do active imaging away from the solar background, and it would allow you to do things. Long wave LiDAR would allow you to image various industrial pollutants, etc., and image in the midwave infrared where there are these new opportunities. I think that I've kind of covered what I wanted to say.
That's great. Thank you very much, Adam. That leads on to one of the questions we've had, but I'll save that to the end. Hopefully we'll have a bit of time at the end just to fire some questions, but linked to regulations around being able to see through things and so on. So we'll come back to that. But for now, I'd like to go to our last presentation, which is from Mark Stevens of Toshiba, based in Cambridge. And this is about cryptography for telecom systems, quantum key distribution, or QKD. So over to you, Mark.
All right, just unmute myself. Okay, thank you for the introduction. Yeah, so yeah, I work at Toshiba Europe Limited, which is in Cambridge. And here are some of my colleagues who've been working on the same sort of things. And so, well, quantum networks kind of encompasses QKD and some other applications. I thought I'd start by just explaining a little about that. And as we heard from David, if you want to secure your data for the future, so not just now, but against more powerful, even classical computers, then really we should be considering quantum security. And the way that that works is, of course, to encode data on single photons, if we're talking about fiber optical networks, because they can't be copied. However, more complex quantum networks, you might want some other applications. For example, quantum computers and quantum processors could be linked together. And also you may want to create links across long stretches, for example, between cities. So you might need quantum repeaters. And for these sort of applications, single photons is not quite enough. You need entangled photons as well. And at Toshiba, yeah, we work on QKD systems, and they're developing, as we've heard, towards commercialization, and then, but also components. For example, these entangled photon light-emitting diodes, which I'm going to talk about more today. So, go to the next slide. So entangled photons are pairs of light particles that share a quantum state. So I've drawn in a little cartoon here what that's for, or the kind of what will happen to those in these networks. And the first thing that happens is that one of the photons will be measured, and by measurement we mean determining its polarization, which is illustrated in this picture here. Light carries polarization, and the image of this watery scene looks different depending on which polarization we're measuring. And when you make that measurement, the outcome of that to that particular photon is random, and that's because these photons exist in a superposition. So, for example, this coin here is spinning. We've heard there's no really good classical analogy of quantum states, but this is mine for today. So it's kind of both heads and tails at the same time, but once it's measured, it becomes a fixed state. But the thing about entanglement is once that happens, then the other photon, in this case, changes to become the same polarization, even if it's far away, which is spooky action at a distance, as Einstein called it. And this is how the various parts of a quantum network can interact with each other through entanglement sharing. So the final ingredient that we'll need is to target a wavelength for these networks, which is where the attenuation in optical fiber is low, so around 1.55 microns in this case. So this is something that we've been doing for a few years, supported by Innovate UK, and also with our partners, the University of Cambridge and Sheffield. And our approach has been based on conventional light-emitting diodes, like these kind of things. But what we do is include some nano emitters inside there, which they're formed from liquid metal droplets. So a bit like these droplets of water on this glass here. And there's an image here of them, how these devices are made. So that it's based on compound semiconductors grown at the University of Sheffield, including those metal droplets, which then we convert to nanocrystals. And then by the end, contacts and stuff are put on for electrical operation, as you would a typical diode, and that's done at the University of Cambridge, and it's all measured by us at Toshiba. So here's an image of a device. This is one of the early ones, telecom LEDs. And when you turn it on, I think it's quite an interesting image. This is under an infrared microscope. So the dimensions here are just a few hundred microns across the image. So it's like a human hair. And you can see all these little light spots, like outside the region, which is this shadow from the anode, and they're individual quantum dots or quantum light emitters, each streaming pairs of entangled photons. And what we can do is navigate this star field to pick one star that we like more than the others, collect that light to an optical fiber, and look for the entanglement signatures that we are interested in. And yeah, we did that. And yeah, these devices are entangled. So anything with fidelity above 50%, it's entangled. So this was a good achievement, we thought, at the time. So to give you a flavor of how those quantum devices are emerging since then, We've had some follow-on projects with the Innovate UK, also with Cambridge and Sheffield, for example, the Aquasec one we heard about earlier. And so here's an example of an application whereby the device is used to generate entangled photons, one sent to a receiver, one sent to be mixed with an input qubit from some sender and destroyed, so it doesn't reveal any information. And that action has the result that the quantum bit that was sent is teleported across the network. And of course, this is one of the primitives that's needed to connect things like quantum computing processes together. Another things we've been working on is developing the quality of these emerging devices. So getting higher frequency operation. Here's an example, for example, of operation of a quantum light emitter of up to 3 gigahertz. And then final slide, just to say that this is also starting to emerge outside the lab. So QKD in itself has been through many field trials and is much more well established, but in terms of entangled photon technology, that's a little earlier in its development stage. But here shows an example where we generated entangled photons from an LED in Toshiba in Cambridge. One was measured to Toshiba and the other sent under the ground through an optical fiber, 15 kilometers in total to the University of Cambridge, where the other photon was measured. And then we can look after that's been done to see if there's entanglement or was entanglement between the two photons. Indeed, the little graph here shows that that's happened. And so we're distributing entangled photons across Cambridge, in this case for, what was it, 14 hours or something. So hopefully that's given you a flavor of the kind of emerging quantum emitter technology here in the UK, and also hopefully convince you that the applications are starting to emerge too for those entangled photons.
That's great. Thank you very much for that, Mark. And thanks to all of our speakers today. Hopefully it's given an overview and clarified that quantum is not just one of these lab mysteries, but really does have real world applications. I'm guessing that there is a question in one of your last slides, Mark, on transportation that could be extended to further transport systems, but we'll leave that one for now. We're slightly over time, so I'd just like to ask a couple of quick questions, and I'll just go specifically to a couple of members of the panel. David, regarding the investment in quantum, just a very quick one there. We had an early question about using quantum for metrology. I think we've covered that in other presentations, but one of the questions was specifically about supporting quantum analog to digital converters. Is that something that's on the roadmap?
Absolutely, yes. So really the integration of these devices onto chip scale is critically important to their deployment. That includes photonic quantum integrated circuits, and absolutely that's part of what we are looking at supporting. It's really, I suppose it's this issue of commercialization and industrialization, the ability to mass produce these devices at a scale where they're useful to be put into products. And that's what really the commercializing quantum technology challenge is about.
That's great, thank you. There was a question about is GPS dead, but I think that was probably answered on the atomic clock presentation, where it talks about enhancing and actually increasing the accuracy of existing GPS GNSS systems. So in effect, it's far from dead. The quantum technologies will really enhance that. We did have a question. Be interested just to get any quick responses if anyone's got a view. Is the brain a quantum computer? Interesting question, I guess, in the form. Any thoughts from anyone on the any speakers?
If no one else is stepping up, I'll just say that I think the answer is we probably don't know. I'm not a biologist, so I won't speculate, but I think that there's still a great deal of research happening about how our brains work and how they function. So whether there's elements of quantum effects involved in how our brains work is probably an open area for discussion. If we had a biologist on the panel, they could probably answer in a bit more detail.
We certainly don't think in ones and zeros, or I guess there's a whole debate there.
I should add, that there is some evidence that there may be quantum effects involved in things like navigation in certain birds that can navigate very accurately, that there may be quantum magnetic effects going on in their brains to allow them to do that. So it's not outside the realm of reality, the question.
Yeah, absolutely. Thank you. And there's another question I don't think we can really answer, but one that's food for thought, and that's more about regulation. Obviously, if we're able to see through, potentially through walls, or potentially start to read minds, this could become one of the barriers, I guess, to widespread adoption until a lot of those issues are sorted out. I don't know if anyone's got any comments on that, but probably quite difficult and outside of our realm.
I think it's critical, and it's one of the areas where the approach we've taken in the UK, where we've joined up all the elements of academia, industry, and government at the start, means that these issues are being dealt with as we go along, rather than running into them and then having to stop while we deal with them. So they are very much on the radar of everyone who's developing quantum technology. We have mostly on the call from NPL, who are very much involved in standards work. And we're also collaborating internationally on that where appropriate, especially on things like communications, where ensuring everybody's working to the same encryption standards and the like is really important to make sure that we're joined up and we're not going to run into those issues later on. Absolutely.
Well, that's great. It's been sorry I've not been able to go through a Q&A session. I had some questions lined up, but we're out of time. I know we've run into the lunch break now before the next session, but I think I'll leave it at that. So I'd like to thank all of the speakers, David, Ali, Moss, Adam, and Mark. And thanks to Technology Connected and to KTN for hosting the session. And hopefully everyone's a little bit more enlightened about the world of quantum and making it real. Thanks very much, everyone. Thank you.
Thank you for joining the Emerging Tech Fest. Join us again on our virtual live sessions, or watch us on playback anytime, anywhere.